All right, let's get right into it. We're going to pull back the curtain on that little bit of digital magic happening in your phone. You know, the thing that tries to figure out what you actually meant to type, even when your thumbs have a mind of their own.
I mean, we've all been there, right? You're texting about a fun family trip to Disney, and a simple typo turns it into a shocking announcement about a divorce. Or, you try to send a sweet text to baby, and it goes to your friend Abby instead. Yeah, that's a whole different level of awkward. So, autocorrect can be a total lifesaver, but sometimes it's like this tiny little monster living in your phone.
So you have to wonder, how does it even begin to guess? It can feel like your phone is reading your mind, or, in those hilarious cases, completely misreading it. But here's the thing, it's not magic. Not at all. It's actually a really clever concept that all boils down to one single super powerful idea.
Okay, so to fix a typo, your phone first needs a way to figure out just how wrong a word is. And it does this by measuring, literally, the distance between your typo and all the possible right words it knows. And this is the key part. It has nothing to do with what the words actually mean. It's all just a numbers game. The system is just counting. It's figuring out the absolute minimum number of steps it would take to change your jumbled up typo into a real legit word. And how does it do this counting? Well, it only has 3 basic moves in its playbook. You can think of it like a little word game with super simple rules. You can either pop a new letter in, take a letter out, or swap one letter for another. That's it. Every single autocorrection you've ever seen is just some combination of those 3 little edits. Okay, let's use a classic example to see how this works, changing kitten to sitting. So first up, we've got to swap that K for an S. Boom, that's one edit. The I and the 2 T's, they're fine, so no cost there. Next, we replace the E with an I. That's our second edit. And finally, we need to add a G to the end. That's edit number 3. So the total distance between kitten and sitting is exactly 3. Now, this works for longer words too. Here, you can see how the same logic applies to a much bigger transformation. The algorithm is just systematically lining up intention and execution and finding the cheapest, most efficient way to get from one to the other, mapping out exactly what needs to be deleted, what needs to be swapped, and what needs to be added. All right, so that's the core idea. Now let's see how this all comes together to create the autocorrect feature we literally use all day, every day. It's actually a really simple 4-step recipe. And this happens in a fraction of a second, right? Your phone goes through these 4 steps. First, it sees a word it doesn't recognize, something not in its dictionary. Then, it brainstorms a whole bunch of possible fixes. After that, it gets rid of all the nonsense words. And finally, it makes its best guess about what you were really trying to say. Let's actually walk through this with an example. Say you type out "my dear friend." Now, our brains, we see dear and we instantly know, oh, they meant dear. A computer doesn't think like that. It just sees dear and says, nope, that word is not in my dictionary. And boom, that's step 1, identify the problem. Okay, on to step 2. Now the system gets busy. It takes Dedra and starts applying those 3 simple edits we talked about, adding, removing, and swapping letters. It generates this massive list of all the words that are just one single edit away. And at this stage, it doesn't care if they're real words or not. It'll come up with dear and dead, but also a bunch of nonsense like dead daya. Step 3 is where the magic really starts to happen. It's the big filter. The system takes that giant list of possibilities and checks it against its dictionary. All the gibberish words, they get thrown right out. What's left is just a small handful of actual valid words. So for our example, we're now down to things like dear, dead, and deal. So now the big question. How does it pick the right one? Well, this brings us to the final and maybe the most important step, probability. The phone looks at the remaining words, dear, dead, deal, and asks which one of these is used the most in everyday language. And of course, the word dear is way, way more common than dead or deal, especially right before the word friend. And that right there is why it all works so well. Based purely on the odds, your phone makes the smart bet that you meant my dear friend, and it avoids suggesting the much more alarming and thankfully much less likely phrase, my dead friend. But wait, how does the computer actually calculate that distance number so incredibly fast? Let's zoom in a bit and look under the hood at the engine that powers this whole thing. It's something called a distance matrix.
To do this, we're going to use a famous method called the Levenshtein distance algorithm. And what it does is pretty genius. It takes a big problem, like finding the distance between play and stay, and it breaks it down into a bunch of tiny, much easier to solve little problems, all laid out in a grid.
So it all starts with building this grid. You put the word you started with down the side, and the word you're trying to get to goes across the top. Filling in that first row and column is super easy. To turn nothing into stay, well, that takes 4 add-a-letter moves, so you just count up 0, 1, 2, 3, 4. And to turn play into nothing, that's 4 delete-a-letter moves. Easy enough, right? Okay, now for the fun part. The algorithm fills in the rest of the grid one square at a time. And the number in each square is basically the cheapest cost to get to that point. To figure out what number to put in a new square, it just looks at its 3 neighbors, the one above, the one to the left, and the one on the diagonal. It asks a simple question. What's the cheapest way here? An insertion, a deletion, or a substitution? It just picks the lowest number from those 3 options and adds 1. Now, see that spot where the 2 A's line up? The cost there is 4. Why? Because the letters match, so there's no penalty for that step. It just pulls the number from the diagonal. The algorithm just keeps doing this simple check over and over, building on the answers it already found until the entire grid is filled. And after all that, the answer to our big question is just sitting there, waiting for us in the bottom right corner. That final number, in this case, 4, that's it. That's the minimum edit distance. It's the total cost of all those tiny little decisions the algorithm made all the way across the grid.
Now, what's really cool is that this powerful idea of measuring the distance between 2 pieces of text, it's not just for fixing typos, not by a long shot. Let's zoom back out for a second and see where else this exact same logic pops up.
I mean, this exact same logic is absolutely critical in some pretty surprising fields. Scientists who study genetics use it to compare DNA sequences to find tiny differences or mutations. Plagiarism detecting software? Yep, it measures the distance between 2 papers to see how similar they are. It's even used by linguists to figure out how languages have changed over hundreds of years, just by comparing the structure of old words to new ones. So the next time your phone saves you from an embarrassing typo, or, creates a hilarious one, you'll know what's really going on behind the scenes. It's not magic. And it's definitely not reading your mind. It's just a really elegant, super efficient, and powerful piece of logic, quietly counting the steps to figure out what you meant to say.